Let me access the answers. So that would be, let's say, the quick answer here, and let's see how many of you have provided that answer. For some reasons, I cannot. Okay. So yes, the quick answer would be that one, C. I also see some other answers, but it's mostly C's. Why? Because we know that in reserves we have how many records? Well, number of records we can fit in a page times number of pages of reserves. And for each of them, we scan S. And obviously this means we read our reserves once, but we read S many times, once for each record of reserves. So one is read just once, the outer relation, but the inner relation is read many times, that many times. But this is, let's say, the surface cost that we might choose here, but it's not the actual cost because obviously we don't read reserves one record at a time. We read it one page at a time. And therefore the cost is reading reserves, so the number of pages of reserves, and then, well, for each page worth of data of reserves, we scan entirely S. So we don't scan naively S for each record of reserves, but for each page of records of reserves. So if you want, we can, it's as if we revisit the approach we had before, and instead of for each record of R, we have for each page of records of R. And then for each page of records of S, we compare the two pages and we find matches in those two pages. And then we continue in this way. Okay, so once again, here the cost would be not this one. That would be, let's say, the immediate response, but it's actually this one because we read from R one page at a time and not just one record at a time. Okay, now a few other questions that we might want to raise here. What if the smaller relation, which is S, was the outer? Would that help? What do you think? What would be the cost? Well, obviously we just flip the cost that we had before, and instead of R times S plus R, we have now R times S plus S. And so if S is smaller than R, obviously we get a small saving here by doing the scan of S in the outer loop instead of the inner loop because of the additive term, which was R before and now it's S and smaller. Okay, so one idea that you can keep from this slide is that if we join relations by this method, and by the way, we call it block nested loop joins or page nested loop joins because we have two nested loops and we read one page from one relation, and for each page of the outer relation we scan entirely the inner relation and so on. So it goes like that for each page of S, scan entirely R, for instance. And in such an approach, block nested loop join or page nested loop join, an equivalent name for it, it's a good idea to use in general the smaller relation as the outer relation, the one that we go over in the outer loop, in the first loop. Second question here, what about when PR, so the number of records in reserves is small? For instance, what if we have, I don't know, jumbo-sized records, very large records in reserves, which take each one page. Each record of reserves occupies entirely one page. What does this change for us, for instance? what should we do now? Well, we might want R instead, the reserves table, to be the outer relation. Why is that? Well, because uh, basically for each page of R, so for each reserves, there is obviously just one sailor that we want to get. Each reservation is done by a single sailor. And so for each reservation, of course, for each page of reserves, we should scan S entirely, but we can, let's say, expect that in average, we will find the one and unique sailor, the right sailor, after reading roughly half of the data, half of S only, right? And so that is the idea, that is, let's say, the intuition why we might want R in this case to be the outer relation, because that will diminish the cost in the end, because we know that for each page of R, we just need to get one record of S. Before that was not the case, and therefore this intuition was not applicable, but here it is. For each page of R, there is a single record of S to get, and we can hope to, through the scan of S, to get it, let's say, in average after just reading half of S and not entirely S. What if S fits entirely in main memory? In that case, obviously, things will be much easier. We just read the small relation that fits in main memory. We have it in main memory, and then we just scan one page at a time from the other relation, and we do the join. So the small relation, the one that fits in main memory, stays there throughout the process all the time. And then we just need to scan one page at a time, the other larger relation. So that's about, let's say, potential choices and ultimately cost when we just apply this naive idea of nested loops. And remember, we will do it with the granularity of pages, and that means that corresponds to the block nested loop join or the page nested loop join. Okay, now in order to make the discussion a bit more precise, when we talk about joins, oftentimes we join by equality on some common attribute. For instance, boat ID, sailor ID in one equals sailor ID in the other. And this is what we call an equality join. And if the attributes that we are putting equality on have the same name, for instance, boat ID in reserves, boat ID in sailors, we will also call it a natural join. Natural join means equality over common attributes. And in our example, of course, with sailors and reserves, we actually do a natural join. They have a common attribute, sailor ID, and we join by that. And so obviously, the natural join is one of the most common cases of joining relations in execution plans. Okay, let's take a break now of 10 minutes. So it's 4:04, so let's say until 4:15. And after the break, we will continue our discussion with other potential implementations of the join operator, and in particular, when we have an index at our disposal. And of course, during the break, feel free to ask questions as well. Okay, so Panopto is recording. Okay, so we left off here, and of course, let me know in the chat window if there is a problem with hearing me or seeing me or seeing the slides. So remember that we mentioned that one of the most common ways of joining relations is by equality on common attributes, the so-called natural join. And of course, equality joins are those that could benefit from an index, for instance, a B plus 3 index. And this brings us, of course, to a second possible implementation. So a second, because the first one that we discussed, of course, was the block nested loop join. So we had, let's say, method number one, block nested loop joins, and now we talk about method number two for joining relations, the index nested loop join. Um, and so we assume here, for instance, that the sailors table has an index on sailor ID, which is of course the primary key of that table, and so it is unique. You see the index here, so you see the let's say uh, the non-leaf nodes of the index, and then the data entries, which are of course at the leaf level of the index. Remember that the leaves of a B plus 3 are doubly chained, and so we have the next previous arrows here. And obviously, we have pointers, record IDs, pointers towards where the actual records are in a heap file. So these are the pages of the heap file for the sailors table with the actual data records. And so you can also see here that the index is not clustered because the arrows pointing to records go in all directions in, let's say, complete chaos. So they are not, we are not assuming here that sailors, for instance, with consecutive ID values will be on the same page. They may appear anywhere in the heap file. So we have an unclustered index on this unique attribute, which is the sailor ID. And we'll see how this can be helpful. Now, of course, looking again at our double loop approach. So for each record or tuple in reserves and for each record or tuple in sailors, if they match, if they have the same sailor ID, we have a record pair for our result. And now, of course, for the matching test, we'll do a lookup in the index. We have with each record from reserves, we get, of course, a sailor ID, and basically we can use that sailor ID as a lookup condition in the index in order to get the corresponding sailor. And so this is our assumption here. So we have a sailor on sailor ID. Everything else remains the same, number of pages, records, and so on. What will be the cost now? Well, it will be the cost of course, accessing, reading the reserves table. So it's this part, of course, plus for each record of reserves, and we have that many of them, the cost of finding matching as tuples. And here we are using the plural, but in fact we know that for a given sailor ID there is a single unique sailor that may match that value. So we should actually have here, to be more precise, finding the matching as tuple. And there was maybe a question. So that will be the cost. And in order to make this cost precise, we have to figure out what will be the cost of matching, of finding the matching as tuples. So it depends on the index in general, of course. If we have an alternative one index, remember alternative one means that we no longer have a separate file for the index and one for the actual data. They're somehow together because in the data entries in the leaf level of the index, we have the actual records instead of just pointers to records. So if it's an alternative one index, well, the cost of finding matching as tuples will simply be the cost of traversing the index from root to leaf, let's say 2 to 4 input outputs, assuming, of course, that the height of the index is rather small. If it's an alternative 2 or 3 index, that means we have to get the actual record from a heap file, from a page in a heap file. And so we'll have the cost of the lookup by by uh, uh, by the Sailor ID, so traversing the tree, let's say 2 to 4 input outputs as before, and then the cost of retrieving records with the corresponding record IDs that we got from the index, and that depends on clustering. So for now here the discussion is general. If it's a clustered index, well, we'll have one input output per page of matching as tuples. If it's an unclustered index, we'll have one input output per matching as tuple. But obviously, we know here that there is a single possible matching as tuple, a single sailor that may have a given sailor ID, and therefore it really doesn't matter whether it is a clustered or unclustered index. Basically, the cost will be one because we'll have just one matching, at most one matching as tuple. And so overall, here the cost, of course, will be R times R plus number of records of reserves times 2 to 4, let's say, plus 1 in order to get the actual record from the sailor's record from the heap file holding the sailor's table. So I hope this is the why here is clear for everyone. Remember that with a clustered index, the data is ordered roughly in the same way as it is in the leaf level of the index, and therefore for each page of matching tuples that we have in the index, we'll get one page, we'll access one page in the heap file. While with an unclustered index, as we assumed in our example here, we may, for each matching tuple, we may get a completely different page. And so we'll pay the cost of one input output per matching tuple. Once again, in our actual example, since the index is on a unique attribute, the primary key, sailor ID, we'll have one matching tuple anyway, so it doesn't make a difference at all whether the index is clustered or not. So what will be the cost? And this is a quick quiz for you. Assuming that on sailors we have an alternative 2, B plus 3 of height 4, what is the input output of joining R and S? And assuming, let's say, yeah, that the root, basically the starting point of the search comes for free. It's as if we have it always saved in main memory because we need to know where to start the lookup, and therefore we don't pay an input output for that. Obviously, A is the answer here, indeed. Okay, and there was a question before, is it guaranteed that using a smaller relation as the outer relation will reduce the cost of any kind of join? It's not guaranteed. It really depends on the case, and we did a kind of a case analysis before. In general, if we have large relations, larger than the available main memory, and in each page of each relation we have many records, yes, it should be a good idea to use the smaller relation as the outer relation if we apply, as the join method, we apply the block nested loop joins, simply because of the additive term. The there is one part that is the same, R times S, but then plus size of the outer relation. And if that's why it should be the smaller relation. Okay, so the answer here is A, and I hope the reason for that is clear for everyone. Now let's look at a different kind of index and let's see what that may lead to. So now we have an index on reserves instead, and let's say we index on the triple sailor ID, boat ID, day in this precise order. So we index, let's say, on values which are concatenations of a sailor ID value, boat ID value, and day. And we want to use this index now in the method of index nested loop joins. Can we use this index? Is it does it lead to, is it better, less costly than what we had before? What do you think? Well, the answer is it depends. And let's see on what more precisely. It depends on the selectivity of the condition that we have here. So depending which relation, so we use the index nested loop joins as the method of joining. But of course, we still have the choice of using S as the outer, R as the inner, or vice versa. If it's S, the outer relation, that means we will use the index on R, of course. And so we access S one page at a time for each record of S, and there are that many records in S. Let me get the pointer. So for each record of S, we search in the index of R and we retrieve from R. If we retrieve one or several records from R, there is the search cost and then the retrieval cost, and they are separate. If R is the outer relation, S the inner, of course, we read R. For each record of R, we search now in the index of S and we retrieve from S. We know that the retrieval of from reserves, we know that the retrieval from sailors, first of all, is just one. For each sailor ID, there is at most one sailor matching that condition. The sailor ID is unique. So the retrieval from sailors was always one. However, the retrieval from reserves, it may depend on our assumptions. For instance, if it's just one, if in average, let's say, for each for each sailor that we are interested in, maybe we don't want all the sailors, but maybe just sailors with rating higher than 5, for instance. If for each sailor that we are interested in average, the number of reservations is 1, so the retrieval cost is 1 page. We have just one reservation to get in average. Then that will be the cost, 500, so size of sailors plus the number of sailors times 5, because once again the search cost is 4 plus 1. While what we had before, using the index on sailors, amounts to this 1,000 pages in reservations times number of reservations, reserves, times 5. Because once again, we have the search cost of 4 plus 1. We get just one matching tuple, one matching sailor. And so we see that the numbers are different. And it would be a good idea, instead of using the index on the unique attribute sailor ID, to use the index on boat ID, sailor ID, and date. Under the assumption that we get, once again, we get just only one matching tuple for a given sailor, in average one reservation. However, if the number of reservations we may get for each sailor in average is different, is larger, for instance, 9. So we expect, let's say that for each sailor with rating 5, we expect to get 9 reservations. In that case, you can see that the numbers change. Of course, the cost of R join S is the same as before, but the cost of S join R becomes much larger because now we have 4 plus 9 instead of 4 plus 1. And now it's a better idea to use R as the outer relation with this index nested loop join. So this is to say that, well, in general, the index may be useful, but we have to understand also what that besides the cost of searching in the index, we also have the cost of retrieval, and that may lead to completely different, let's say, performance for a join using an index. Okay, now we have seen how we can join by simply reading the data with blocks nested loop joins. We have also seen how we can join by using an index when an index is present. And we also compared between two different situations, different indexes. Now we'll talk about a different method for joining, which relies on sorting. Another way, once again, of implementing the relational operator, which is the join. So it works for equality joins, so equijoins and natural joins. Remember, natural join is one in which the equality is on common attributes, attributes having the same name. And it works in two stages. We sort the tuples, the records in the two relations by the join key. For instance, the sailor ID. And then that means, of course, that all the records having the same key will appear one next to the other. And sometimes the sorting may be done already. For instance, if this is the result of some other operator. And then we will scan the sorted partitions of the two relations and get records that match, get join results. So let's see how this goes. And we'll have first of all an illustration for that. So these are the two, let's say, relations. We have sailor ID, sailor name, sailor ID, boat ID. And you can see that, of course, they are sorted by the common attribute, the sailor ID. And it's as if we have a reading head on each of them, initially placed on the first record. And we compare at all steps, we compare the values, sailor ID, that we have at the position of each of the two reading heads. So for instance, now in the beginning, we don't have records that join. So we have nested loops as well. And here, since 22 is less than 28, we advance here. And now we have 28 on both sides. So we do have a join result. This one. Okay. Now we continue and we advance in the other relation. We have another join result. Two pairs of records that should join. We continue advancing in the reserves table, and now we have distinct values, 28 and 31. And so, of course, we have to see if there are also other 28 sailors in sailors. So now we go back to where we were and we advance in sailors. But now we have 31 and 28, so we can safely advance here. We have again matching tuples that lead to joint results. And you can see how this goes. So basically we have these reading heads and they advance synchronized in a certain sense in such a way that we make sure that all the matching records are found. And of course for that we exploit the fact that the two relations have been sorted before by the sailor ID, by the join attribute. So this is the general idea of sort, merge, join. And of course, we advance ultimately the two reading heads until basically we have reached the end of the two relations. Now, what would be the cost of all that? Uh, if you think about it, of course, we have to first sort the data. And we know already what may be the cost of that. Um, we have the R relation, we have the S relation, and of course we need to sort them. So we have the cost of sorting each, and then we could expect that the sort of the merge afterwards is roughly R plus S. That's, let's say, general, a bit optimistic assumption, but there is a worst case scenario in which, in fact, this last term is not just R plus S, number of pages of R plus number of pages of S, but in fact, the product of the two, R times S. In fact, we'll read for each page of one, we'll have to read each page of the other. Instead of just reading, scanning roughly once the R relation and then scanning roughly once the S relation. So what would be this worst case in which the cost of the last of the merge stage would be actually R times S? What do you think would be a worst case scenario in which the cost of this merge will be R times S, in the sense that for each page of one we'll have to read each page of the other? No common? No. All the same, exactly. If we just have the same single sailor ID value in all the records from the two relations, then of course they all join, and therefore we need to basically for each page of one we have to read each page of the other and to compute join results. So all the same, or at least very few values that are found, let's say, in all records. So that would be a worst case scenario. So a question. So this is of course the big picture on how we do this sort merge join. So we read and sort R, we read and sort S. We have the sorted runs that then initially sorted runs from R and sorted runs from S. We merge B minus one at a time. Remember, we have B pages. We merge B minus one sorted runs from, let's say, pass 0. We get the sorted files for R and S separately, and then we read them and we merge once again with B minus one input buffers and an output buffer. Now, there is something strange that you may have or may not have noticed here. Remember how we did the sort external sort algorithm. In phase one, we were reading batches of B pages, sorting them and then merging them later in phase one. So in phase 0, we were producing batches of size B of sorted data, runs of size B of sorted data. But here, phase 0 is different. Instead of B buffers, in which we read B pages from R or B pages from S, we have B minus 2 buffers, and 2 buffers are left for output. This is just an indication that here we are using a different, a slightly different, let's say, external sort method that is discussed in detail in the cow book. It's a technique called replacement sort. And it's simply, let's say, an optimization on that allows us to produce longer sorted runs at phase 0, longer than just B pages. In fact, it can help us to get sorted runs of size 2 times B instead of just B in average. So if you want to learn about the replacement sort, you can read about it in the cow book. But anyhow, regardless of whether we use just we sort B pages at a time in phase 0, or we use this optimization that is replacement sort, we basically, of course, overall the cost is the same. We sort R, we sort S. It's just that basically we may be able, with the latter, with replacement sort, we may be able to sort larger data sets with just two passes, because it allows us to get longer sorted runs at phase 0. And another remark here, obviously the join result is when we apply this method, sort merge join, the join result is sorted on the join attribute. And this may be, of course, quite useful later on. So this can be seen as an additional advantage of the sort merge join. For instance, we may want to display the result of the join in order, and that comes by design with the sort merge join, and not necessarily with other techniques like block nested loop joins, for instance. Okay, so yeah, so regarding this question, how big does the buffer have to be to sort R and S into two passes each? Well, remember that we discussed this, and B has to be larger than the square root of the largest relation, so max of R and S. In this way, both of them can be sorted in just two passes, as illustrated here. We have here two passes for sorting and then one pass for merging. And in that case, the cost will be the cost of sorting R. So remember, two passes, so 2 times 2, because we read and write at each pass, times size of R, plus 4 times size of S. So that's the sorting part for R, sorting part for S, and then sum of the two as indicated here in the, let's say, average cost or optimistic cost. So that would be the cost of merging this, joining these two tables by sort merge join. 7,500 input outputs. Compare that with the previous cost that we had, which was, of course, order of 200,000, right, when we were using the index. So much more interesting. Okay, now assuming that we might need a sorted result anyway out of the join. For instance, we just want to display the result of the join and we want to display it in order. Assuming, for instance, we have this query, select from R and S where they have the join condition on the common attribute sailor ID, order by sailor ID. Assuming also that we have, as before, B blocks at our disposal, let's see what may be a good idea. For instance, what if we use block nested loop joins, or what if we use sort merge join? And let's see when it might be a good idea to use one or the other. Once again, assuming now that the result of the join needs to be ordered anyway. So the question here otherwise may be, might it be, let's say, a better idea or a good idea to join first and sort later, or to sort first and then join with sort merge join and get by design the result, the join result ordered as well. So the block nested loop join, of course, we know it by now, but so what we discussed until now was a situation in which we were reading one page at a time from the outer relation. But we don't need to do just one page at a time from the outer relation. We can read b minus 2 pages at a time from the outer relation. Why b minus 2? Because we leave one page for reading from the inner relation, from S, and we leave one page for writing output, for writing join results. Okay, so this is why basically we can, the most we can do is basically read chunks of b minus 2 pages from the outer relation. Let's say from S sailors here. Remember, we said that it's a better idea to use the smaller relation as the outer. So for each chunk of size b minus 2 pages from S, and we have that many of them, of course, we'll have to scan R. We have to read entirely R. Okay, so therefore we need to read R that many times. And obviously we will read S, the outer relation, just once. So we read S once, but in chunks of b minus 2 pages. And for each chunk of b minus 2 pages, we read one page at a time R, we scan one page at a time R, and we compute joins. So that would be the cost of the block nested loop join, assuming that we have b pages at our disposal. We use b minus 2 for reading from the outer relation, 1 from reading from the inner relation, and 1 for the output. So that will be the cost of joining. What will be the cost of sorting? Well, the result, let's say, will be roughly size of R. And so it will be this one, 2 times size of R plus the number of passes that are necessary. And that, of course, depends on the size of R on one hand and on B on the other hand. We know that we have this formula for the number of passes, pass 0 plus that many passes to merge sorted runs from the previous stage. So, for instance, if B is 102, and that means that B minus 2 is 100, we end up with this cost. The join, if you do the math, we know the size of S, 1000, if I'm not mistaken, divided by, 500 divided by 100 times 1000 plus 500. So 5000 plus 500. The sort afterwards will be this, 2 times size of R, 1000, so 2000 times 2. So 4000. So overall 9500 if we are in this situation where we need to join and then the result must be ordered, and we do it by first joining and then sorting, ordering. What about the sort merge join? What if we sort first and then join? In that case, the cost of sorting will be this. The cost of sorting R and S respectively will be this and this. And then the cost of the join will be this, and therefore that will be the total, which is of course better than what we had before. So you can see that depending on the context, depending on the situation, if we may need to order anyway the result of the join or not, we may pick one or the other of the two methods. Sort merge join has this cost, but if we don't need, of course, the result to be ordered, we might as well use block nested loop joins because the cost is less than that. Okay. So if the result of the join has to be ordered, sort merge join is the better option. If the result of the join doesn't necessarily have to be ordered, here the block nested loop joins is the better idea. Okay, now regarding the sort merge join approach, so we have seen this, let's say, big picture in which we have a phase 0 and then phase 1 for sorting R, same for sorting S, and once we have the sorted relation R, the sorted relation S, we merge them in the merging phase. But there is an important refinement that can be done here that basically brings the merging earlier, but it needs more buffers. It needs 2 times more buffers. And that works in the following way. We do the join during, let's say, the final merge pass of the sort. So we read R and sort chunks of R and write them, of course, and that is pass 0. We do the same for S. But then, so remember the merging stage of sorting, we merge R runs and S runs, and at the same time we find join matches between the two. And in that case, the cost will be just 3 times R and plus 3 times S, so a bit less than what we had before. But this, let's say, assumes assumes that the memory is greater than square root of r on one hand and square root of s on the other hand. In that way, we have, let's say, we can have one input buffer for each run of R that comes out of phase 0, and for each run of S that come out of phase of pass 0 for S. And then we merge, let's say, at the same time, we merge the runs of R. We also merge the runs of S. And we also are able to write output of the join. Merge basically in the join, in the sense of joining this resulting R and S output streams as they are generated. So that of course requires twice more buffers because we merge the sorted runs from R and S at the same time instead of separately, let's say. Okay, so it's time for a quick quiz for you. When is sort merge join a pretty good idea? When one or both inputs are already sorted on the join attribute, we are running an arbitrary theta join. So theta join is simply a name for an arbitrary join condition, not necessarily an equality. Could be I don't know, both ID higher than rating from sailors. Any condition that looks at two values of two attributes and test something on them. So that's a theta join. So not necessarily equality, not necessarily equality on common attributes. An arbitrary join condition. The output needs to be sorted on the join attributes. None of the above. What do you think? Is A true, for instance? C is obviously true, and it was the topic of our discussion just before. If the output needs to be sorted on the join attribute, then sort merge join may be a good idea. A is also true, of course, because if one of both of the inputs are already sorted, then we don't have to pay for the sorting. We don't incur the cost of sorting, and therefore the overall cost will be more interesting. So here, indeed, A and C are the right answers. Obviously, sort merge join works only for equality joins, so not for arbitrary theta joins. And therefore, that's the explanation here. Okay, so now we'll move to a new kind of join, a new kind of join algorithm, one that uses hashing. The so-called hash join or grace hash join algorithm. So now the idea is to simply, let's say, identify, it also works for equality predicates, by the way, so equijoins or natural joins. And the general idea, and so we'll first talk about a naive approach with very, let's say, powerful limitations, and then we'll talk about the generalization of it. But the general idea of the naive hash join and of the grace hash join is that we, on the joining relations, will identify partitions by hashing instead of sorting, as we did before. And so we'll start with a naive approach that works in a corner case in which R is the outer relation, let's say, is really small, is that's so small that it fits in main memory. In that case, we can load R in main memory and build a hash table for it. Let's say we use for that as many buffers as we can, namely B-1, B-2 buffers. By now you should know the drill. Why b minus 2? Because we leave one buffer page for reading one page at a time from the other relation from S, and one page for writing output. And so the remaining b minus 2, we use them for building a hash table for R, assuming that b minus 2 is enough, assuming that R is small enough to do that. And then we scan S one page at a time, and for each record we probe into the hash table. So we just apply the same hash function, and basically the hash function will tell us if we have matching records or not in R. We probe the hash table and we find matching tuples, join results that we write in the output buffer, and then of course we save whenever this is full, we spill it to disk and we save the results. What will be the memory requirement for that? Well, R has to be small enough to fit in a hash table of b minus 2 pages. And obviously, R should be significantly, I would say, less than b minus 2 because there is, let's say, a parameter, the hash fill, which says that basically, well, the data will not be evenly distributed in the various buckets of the hash table. Some may be larger than others, and so we'll need basically uh, a hash table that is more than just R itself. So this is why R has to be b minus 2 times a hash fill, let's say, parameter. So obviously the question now, so this can work very well, assuming that R is for instance, the hash fill may be 0.9 or 0.8. So assuming that R is a bit less than b minus 2, the available memory space for it. If this is not the case, then of course we need to generalize this idea. And to do such a generalization, we can rely on some useful properties that we'll discuss next. So sometimes, even if R is not small enough, let's say, we may be able to break it into parts or into partitions that are small or small enough. For instance, forgetting about hash join for an instant, if we need to join R and S, but then only some few sailor ID values are of interest, for instance, just 4 and 6. Well, we could break our join, of course, into smaller separate computations. In this example, instead of um, uh, joining by all sailor IDs, since we only care about two distinct ones, we could end up with two significantly smaller joins that must be done instead of a larger one. One for sailor ID 4 and one for sailor ID 6. Two smaller joins, since in each part of the union that we have here, we can first push this condition, sailor ID equals 4 on R. We can say, actually from R, I don't want all reservations. I only care about those for sailor ID 4, and here as well, I only care about those for sailor ID 6. And so we can do the selection by sailor ID before we do the join. The same idea, if you want, could apply everywhere if we hash the sailor ID first. So we want now, of course, to join R and S, and we have a condition on the hash of the sailor ID instead of the sailor ID itself directly. And maybe, once again, the hash of the sailor ID has fewer, significantly fewer, let's say, distinct values than the attribute sailor ID. Remember that we had, for instance, in sailors, we had 40,000 sailors. So 40,000 different sailor ID values. But maybe the hash of sailor ID will give us only 100 distinct values. 100 values for hash of sailor ID. So that will be the idea that can be applied here, the property that can be applied here, following the example that we had before. If we want to join, but we only care about a few values for the join attribute, then we can get away easily with that. And here we will apply the same idea. Even if we want to join on all the possible sailor IDs, we first transpose that domain, sailor IDs, into a smaller domain by hash of sailor ID, and then we solve the problem on each of these distinct and few hash of sailor ID values. So it's as if we have now a hash of sailor ID attribute or some kind of function map, an application of the hash function on each record from these two tables that basically takes the sailor ID attribute of each record and leads to a different attribute that is not sailor ID anymore, but hash of sailor ID now. And in doing so, once again, we end up with two relations. Let's call them RH and SH, that instead of sailor ID and many values for sailor ID, have hash of sailor ID as the join attribute and a join attribute with significantly fewer values. Instead of, for instance, 40,000 different values, we may have just 100 different values for this new join attribute. And so just like in the, let's say in the example before, we can assume that we have significantly fewer hash sailor ID values than sailor ID itself, for instance, 100 instead of 40,000. And then we can join in separation R and S for each of these 100 distinct hash sailor ID values. So this is the idea that we will follow here. With the hash join or the Grace hash join, we will partition the relations by a hash function so that we end up with smaller joins to be computed, small enough, let's say, to be amenable to the naive hash join that we saw before, where R was really small, let's say. And so this idea can be applied once or may even be applied several times recursively, as many times as necessary, until we end up with, let's say, small enough partitions in order to apply the naive hash join that we started with. So let's see how it works on an example, and things will become more clear for sure. So it requires, once again, an equality predicate. So it only works for equijoins and natural joins. And so there will be two stages. We will partition the tuples from R and S by the join key. So by hashing them on the join attribute using, of course, the same hash function. This is important to remember here, the same hash function. Obviously, if we hash each relation into k partitions rather uniformly, let's say, we can be sure that our tuples from one partition, let's say from partition 5 or from bucket 5, can only join with S tuples from its own partition 5. So that will be the idea here. Then we'll have to solve the join problem only by working on corresponding partitions. Partition 1 from R can only join with partition 1 from S. Partition 2 from R can only join with partition 2 from S, and so on. So that will be done afterwards with the conquer stage, in which we apply, for instance, naive hash join, assuming that the partition of the smaller relation now fits in main memory entirely. We can then use naive hash join on partitions of R and S. So Grace hash join does partitioning with her first, let's say, hash function. Let's call it H1. Then naive hash join is applied on pairs of partitions from R and S with a second hash function. Let's call it H2. And so we'll see the, let's say, the details in a running example soon. Obviously, if you wonder how we do the first stage, the partitioning by hashing, we have learned about that, of course, just before. So we used, of course, we can use external hashing, the method that we saw before. So remember that with external hashing, we read one page at a time from the relation we want to hash. We have b-1 buckets, so the hashing function can take input into b-1 different partitions. That ultimately leads to b-1 partitions, each of size roughly n divided by b-1, and then of course we can conquer then each of these stages in assuming that each of these partitions fits now in main memory. So in a total of b buffer pages, we can solve the hashing now entirely one partition at a time. With the first stage, remember what is guaranteed is that matching tuples, so records, for instance, having the same sailor ID, end up in the same partition, not necessarily one next to the other, but in the same partition. And then with the second stage, we now make sure that matching records are one next to the other, are grouped. Okay, so let's look at an example now. Let's run, let's say, the external. Actually, so no, this is an example on external hashing. As a way to recall what we have discussed before, so I will skip it here. So this animation, I would say, is rather useful as a complete example on how external hashing works. So I encourage you to go over it later on. I will go over it rather quickly now. Okay, up, conquer. Okay, and now we are with where we wanted to be. Oops, sorry. Okay, so now about Grace hash join. Of course, we so again, what was before is just a parenthesis on external hashing, running it over an example. We apply this external hashing idea on both R and S. So we have here the blue relation, let's say R, and the yellow relation S. And remember that it gives us, external hashing gives us partitions, b-1 partitions for R, b-1 partitions for S. And now, assuming that, let's say, the blue relation is the smaller one, and so partitions of reserves one at a time can fit in b-2 pages, the hash table of such a partition can fit in b-2 pages, then we can apply naive hashing. So basically, we read one partition from R, we build its hash table in the b-2 pages, and then since partition 1 can only join with records from partition 1 of reserves, by design can only join with records from partition 1 of sailors, then we read basically one page at a time from partition 1 and we write join results in the output buffer. All this works once again because we are using here the same hash function in the hashing stage on the two relations. And that of course guarantees that records from partition 1 of reserves can only join with records from partition 1 of sailors. Records from partition b-1 of reserves can only join with records from partition b-1 of sailors. So that's the general idea here. And so after the divide stage, we conquer by using the naive join algorithm that we started with, which assumes that each of these partitions of the smaller relation, let's say, can fit in a hash table of size b-2. Okay, so it's as if we have the partitions, let's say, lined up, and we know that at each stage, basically, we have to work with just a pair of partitions. Partition 1 from R, partition 1 from S, then partition 2 from R, and partition 2 from S, and so on. Okay, so this is basically the let's say the pseudocode for Grace hash. Following this idea. And this is once again an animation for this method. So I will also skip it now, but I encourage you to look at it later on at home. So it follows exactly the, the, the general lines that we saw before. We have the two relations R and S. We build the partitions first, and then we conquer by working with pairs of partitions. So I encourage you to look at this later on at home as well. Or maybe, okay, let's look at it together. I just want to make sure everything is clear here. So let's say we have B minus B buffers as before. So we read one page from S. We have B minus one possible partitions or buckets where each record can go. And obviously here the colors indicate values. So only records with the same color can join. So for instance, let's say the hashing takes them in this way. And obviously in a partition, we may have records with different values. Okay, we read the second page from S. And once again, we apply hashing. So the green records go here, the purple and yellow go here. This one is already full, so we have to split it to disk, the other one too. Okay, and we have just partitioned S. We have two partitions. Let's say assuming that, of course, B equals 3 here. We do the same for R. Remember, yellow goes in the second partition as purple, and green goes in the first partition. And remember, we are using this exactly the same hash function. We read this next page of R, and again, green and gray go here, and yellow here. Okay, and so now we have just partitioned both R and S, and we have put, let's say, the partitions one next to the other. So we have here partition 1 for S, partition 1 for R. We have here partition 2 for S and partition 2 for R. Okay, so the partitions, partition 1 is 1 page in size for both R and S, while partition 2 is 2 pages in size for both S and R. Okay, now we conquer. Yeah, so for instance, here you can see that, for instance, there is a bit of skew. Some values are more frequent than others. For instance, the fuchsia or purple values here are more frequent, and that leads ultimately to larger partitions. And that may be problematic in some sense. But let's continue our example. So now, remember, we take the smaller relation. In our case, let's say R. So now let's deal with partition 1 first from R and S. We take partition 1 of R. We build the hash table for it. And then we read one page at a time from S. And we probe the hash table in order to find join results. For instance, for green, we have found not one, but two joining records in R. And so we have two join results. For this one, we have one, and for this one, once again, we have two. We have one page of output that can be saved to disk, let's say. And we are done actually with partition 1 from R and S. And now we move to partition 2. We build another hash table for it. of course, the partition 2 of R, the smaller relation, and then we read one page at a time from partition 2 of S. We probe in the hash table and we get, once again, output results. And we do the same here with the remaining page of partition 2 in S. And that's basically the flow of the Grace hash join. Okay, so as a summary for Grace hash join, and there's a cost analysis. So what is the cost of all this? Well, uh, obviously we have the partitioning phase, and maybe there is a question. Yes, of course, in video format you will have it with the recordings of the class. That should help as well. So the partitioning phase, of course, for R and S means, for instance, if we get away with just two passes, means 2 times R and S, read write both relations. And the matching phase, read both relations once, basically, so the overall cost will be 3 times size of R plus size of S. So, for instance, 4,500 input outputs. In order to make, let's say, this cost analysis a bit more precise, since we rarely go all the way to explain how much time this might take, for instance, let's do it here. Let's assume that we access pages with 10 milliseconds per page, but maybe probably much faster because we can assume that we access pages sequentially. So that will mean, for instance, 45 seconds. So that may be rather fast or rather slow, depending on your expectations, let's say. But the good news, I would say, is that overall it should be actually much faster because we can expect that we access data, the pages of R&S sequentially, so without a seek overhead. And so this latency of 10 milliseconds is actually much too high. So overall, joining these two relations should be much faster. Okay, now regarding the memory requirements, or how much data can we deal with depending on the number of passes. So remember that we had a condition for we had a condition for the smaller relation, right? After the partitioning phase, which divides R, the smaller relation, into B minus 1 runs, that large, let's say in size, assuming they are uniformly large, they have the same size. The second stage, in order to apply naive hashing, we have to assume that each partition fits in B minus 2 pages, in a hash table of B minus 2 pages. And so the condition is the following: the smaller relation R has to be less than B minus 1 times B minus 2, so less than B squared, roughly. So when R is less than B squared, roughly, we can apply the Grace hash join and get away with just 2 passes as we saw before. We partition the two relations and then we use partitions we build hash tables for partitions of the smaller relation R, and we get 1 page at a time from the other relation, just as we did before. So the memory requirement for that would be that the smaller relation R is less than B squared. So basically we have the following situation now. We have 2 options. Let's say depending on how large R, large, let's say, the smaller relation R is. If R is less than B squared, we can use Grace hash join. If R is actually less than B, then we can use directly naive hash join. We don't need to use Grace hash join. We just put entirely R in a hash table. as we saw before. Now the question may be what happens in between? What if R is larger than B, so we cannot use naive hash, but less than B square? Because for now, basically the situation is the following. If R is at most B, we can get away with just naive hash, so one pass. If R is between B and B square, well, we have to use Grace hash. And so we have, let's say, a complexity jump or a cost jump between one and two passes. And the question is, do we really have to pay this jump as a step, let's say, in the cost function, or can we, and obviously the cost will be n here, just reading all the data once with naive hashing, and free n with Grace hash. So it's a steep, let's say, increase in cost depending on the size of R. And the question is, can we pay this increase in cost in a more, let's say, gradual manner instead of just jumping from n to free n? And the answer for that is yes, we can. There is let's say, a hybrid approach that follows, let's say, a gradual cost increase depending on the size of R between B and B square, which avoids this cost jump from n when we are less than B to free n directly when we are higher than B. So this is called the hybrid hash method. We will not discuss it here, but you should know it exists. And if you want to learn more about it, of course, you can look for it in the COW book. So we have seen now, let's say, as a final summary on the various join algorithms that we have discussed. We have seen page nested loop joins where we read one page at a time from the outer relation, block nested loop join when we read chunks of B minus 2 pages from the outer relation. We have seen index nested loop joins. We have seen sort merge join using the idea of sorting first and then joining. And we have finally seen the hash join that uses the hashing idea. So how do they compare? And well, you should know that there are, let's say, no clear winners here. There is no approach or method that is absolute best, always better than the others. It really depends, let's say, on the data, on the computing environment, for instance, what is the size of B compared with the size of the data. And there, for instance, a very simple exercise can illustrate that depending on the size of B and the size of the data, for instance, block nested loop join may perform better or worse than sort merge join. So there are some, let's say, advantages for the sort merge join algorithm and the sorting idea. It's a good idea, for instance, if the input may already be sorted, at least partially, or we need the output to be sorted. It's not sensitive to data skew, to some values on the join attribute being much more frequent than others, or to bad hash functions. Regarding the hash join method or the Grace hash join method, it can be cheaper due to this hybrid hashing idea that we mentioned before, in which the cost goes gradually from n to free n instead of a steep jump. And also the number of passes depends on the size of the smaller relation, right? That was the discussion we had before. And it may happen that, well, there is an unbalance and one relation is significantly smaller than the other. And it's also good, of course, if the input is already hashed or we need the output to be grouped or hashed anyway. Okay, so as a final summary, let's say, so we have seen various methods for computing joins, nested loop joins that work for arbitrary join conditions, so theta joins, index nested loop joins that work for equi-joins, and of course assume that we have an index that can be used, and then sort and hash joins also for equi-joins but without requiring an index, for instance. And obviously, remember, there are no clear winners. one, and well, when we say one here, of course, it means any relational database management system should implement all of them, should have implementations available for all of them that can be used depending on the situation, depending on the execution plan in which we have a join, depending on the configuration, size of the available main memory, and so on. All implementations should be available in such a way that the system can pick the best one for a given situation. And of course, what you should know here is the cost of each, the cost model for each, because you will need that when we'll talk about query optimization and when we will do, of course, also the practical assignment with Oracle on query optimization. Okay, so what comes next? So I will stop here for today's discussion. And so what comes next are some extra slides on this hybrid hash join method that we mentioned before. And once again, it's a method that is also discussed in the code book. So if you want to learn more about it, feel free to look at these extra slides as well. Okay, so it's almost time for today, so we will stop here. Just a final reminder that you should uh, look at the Docker installation indications that we have put on Moodle, so that you have everything ready for the practical assignments. So the first practical assignment on query optimization with Oracle will be released next week, after the class of next week. You'll have 2 weeks in order to complete it, and you will need you will need Docker and an Oracle, a Docker Oracle image for that practical assignment. So if you have not done yet this part, read the instructions for installing Docker and the various images, and also, very important, answer the poll that we have on Moodle about that. Tell us what may be the difficulties that you have encountered, and do not hesitate to send us an email if you have problems with the installation of Docker. And if they cannot be solved by email, you may even consider coming on campus and meeting one of the TAs in order to figure out together how to solve this kind of problems. Okay, so we will stop here for today. Thank you all for attending. And there is a final question on page 29. Why the sort of R rather the result of join R and S? We do the join first and then sort. Okay, so that's about the situation where we needed the join result to be sorted anyway, and we were comparing block nested loop joins with sort merge join. Okay. Oh, I see. Why sort of R and not, okay, so yeah, because we assume here basically, yeah, we assume that, maybe I forgot to mention this, we assume that the result of the join is size of R. And this makes sense here because obviously, so we join sailors with reserves. For each reserves, we have a corresponding sailor. So the result of the join is size of R. And that's what we need to sort after the join. While when we sort first, we need to sort both R and S. And so we we have a sorting price for both of them. That's the explanation. Not size of maximal one. Here, actually, we had a precise example in which we were joining reserves and sailor by sailor ID. So if you think about it, because we wanted basically for each reservation, we wanted the name of the sailor and the reservation description and so on. But actually, this query does what? It takes the reserves table and it enriches that table with information from sailors, the name of the sailor in particular. But ultimately, it's still the size of the reserves table. For each reserves table now, besides sailor ID, boat ID, day, and reservation name, we also have the sailor name. That's what we get from the join. This is why the result of the join is actually precisely exactly the size of reserves. It's reserves plus some more attributes. So this is why we say it's the size of reserves. Okay, and this is why the sort will considers that as a cost. While sorting before joining, of course, means sorting both R and S. Okay, so in this example, basically, of course, for each reservation, we have one corresponding sailor, a single sailor, by sailor ID. And basically, it's as if we take the reserves table and we just add a few more attributes to each of its records, in particular, the sailor name. And that will be the result of the join. Okay, so thank you all for attending once again. And of course, at 6 I will move to, at 6 p.m. I will move to the office hours Zoom meeting where you can enter one by one and you can ask your questions. Thank you all and see you next week.